3 days ago, a PDF appeared on an encrypted forum. 37 pages of Hubble data. Page 19, red text, secondary signature detected, do not distribute. 6 hours later, the file vanished. Servers wiped, but 1,847 people had already downloaded it. And what those pages show about the object flying next to Comet 3 I/Atlas has scientists breaking silence. Amateurs trading theories, and one Harvard physicist asking, what if this isn't a comet tonight? We're going where NASA won't. If you're hooked already, like and subscribe, but only when you mean it. Tell me in the comments where you are and what time you're listening. I actually read them. Share this if someone needs to hear it. Now kill the lights, settle in, and let's uncover what they tried to bury. The file hit the servers at 2:47 AM Eastern Time on October 18th, 2025. You know, that oddly specific timestamp because the metadata was still embedded in the PDF when it first appeared. Someone at NASA's Jet Propulsion Laboratory either got sloppy or wanted to be found. Either way, within minutes, a small corner of the internet that most people don't even know exists was absolutely losing its mind. The forum where it dropped isn't your typical Reddit thread or Facebook group. We're talking about an encrypted message board used by amateur astronomers, retired aerospace engineers, and the kind of people who track satellites for fun. The post itself was simple. No dramatic message, no manifesto, just a download link and 3 words. Look at page 19. By 3:15 AM, 17 people had opened the file. By dawn, that number hit 1,847, and then, just as suddenly as it appeared, everything vanished. The original post, deleted. The user account, gone. The backup server in Iceland that hosted the PDF completely wiped. But here's the thing about the internet. Once something escapes, you can never really put it back in the bottle. So what was in those 37 pages that made someone risk their career, possibly their freedom, to get it into public hands? The document opens with standard Hubble Space Telescope observation logs. If you've never seen raw space data before, imagine the world's most boring spreadsheet had a baby with an Excel file from 1997. Columns of numbers, timestamps, wavelength measurements. This is the stuff that gets analysed by software first, then reviewed by grad students at 3 AM surviving on coffee and the faint hope of one day getting tenure. But page 19 is where everything changes. Have you ever been reading something perfectly mundane and then suddenly a sentence makes you stop and reread it 3 times? That's what happened to those first 17 people. Right there. In the middle of routine observations of Comet 3 I/Atlas taken between March 8th and March 22nd. 2020, there's a notation that doesn't belong. It's in a different font. The rest of the document uses Courier News standard NASA formatting since approximately the invention of computers. But this note Times New Roman, 14-point, bold, and in red text that practically screams someone added this later. Secondary signature detected at 0.31 arcseconds offset. Magnitude variance suggests non-cometary albedo. Flagged for ITAR review. Do not distribute. Let me translate that for you. Someone at Hubble, while photographing a comet, caught something else in the frame. Something close enough to the comet to be travelling with it, but different enough that it didn't look like a chunk of ice and rock. And then someone classified it under ITAR, the International Traffic in Arms Regulations, which is the legal framework the US government uses to control information about defence and space technology. Why would you classify an observation of a comet under weapons regulations? Now, 0.31 arcseconds might sound tiny, and it is. We're talking about an angular separation roughly equivalent to spotting a dime from 2 miles away. But in space terms, at the distance 3/Atlas was from Earth in March 2020 that translates to approximately 50,000 kilometres of actual separation. For context, The International Space Station orbits about 400 kilometers above Earth. This object, whatever it was travelling alongside the comet at a distance greater than the circumference of our entire planet. The leaked data includes 4 separate observation sessions, March 8th, 11th, 18th and 22nd. Each time Hubble's Wide Field Camera 3 was pointed at Atlas. That secondary signature appeared. Same relative position, same unexplained brightness. And here's where it gets interesting between March 18th and March 22nd. The comet started breaking apart. Fragmentation is normal for comets that get too close to the sun. The ice sublimates, internal pressure builds, and eventually the whole thing just shatters like dropping an ice cube into hot coffee. But the secondary object, still there, same distance, same trajectory, moving through the debris field like it was following a GPS route while everything around it was falling apart. Think about that for a second. Imagine you're watching 2 cars drive down the highway side by side. One of them hits a massive pothole, explodes, and breaks into pieces across 3 lanes. The other car doesn't even flinch, just keeps cruising at the exact same speed in the exact same lane. You'd probably have some questions about that second car. Right, the leaked document includes spectroscopic data, which is basically a fingerprint of what something is made of based on how it reflects light. Atlas's nucleus showed exactly what you'd expect water ice signatures. Rocky silicates, organic compounds, standard dirty snowball composition. The companion object. The spectroscopy line flat out doesn't match. The albedo, the measure of how reflective something is, came in at around 0.12. Atlas's icy nucleus was reflecting at about 0.04. This thing was 3 times more reflective than the comet it was travelling with. The person who leaked this included handwritten notes in the margins, not digital annotations, actual pen on paper that was then scanned. Which tells you this document lived as a physical printout somewhere before it went digital. One note, scribbled next to the spectroscopy data, reads checked calibration 6X, not instrument error, not ghost image, real. Another note, on page 23. If not natural, what clearance level decides when public has right to know? That's the question. Isn't it at what point does scientific discovery become classified information? NASA's official position on leaked documents is straightforward. They don't comment on unverified materials from unknown sources. But within 48 hours of the PDF hitting that forum, something interesting happened. The Hubble Space Telescope's observation schedule, which is publicly available and updated weekly, showed a sudden gap. 6 hours of scheduled observations on October 21st just disappeared, replaced with instrument maintenance. Funny timing for maintenance, don't you think? Here's what we know for certain. The observation data is real. Multiple amateur astronomers have verified the timestamps and positional data against known locations of 3I/Atlas during March 2020. The numbers check out. This isn't some kid in a basement making up fake data. This came from inside. What we don't know is why it stayed buried for 5 years. Atlas fragmented in April 2020. By May, it was basically a fading cloud of ice crystals. Papers were published. Data was archived. Everyone moved on. Everyone except, apparently, whoever wrote those margin notes. But before we can judge whether NASA was right to keep this quiet, we need to understand what 3I/Atlas actually was. Because here's the thing, it wasn't even a true interstellar object. Not technically. And that detail, that's where this story gets really weird. So let's clear something up right now, because the name 3I/Atlas is deliberately misleading. That I stands for interstellar, and technically speaking, this comet was nothing of the sort. When you hear interstellar object, your mind probably jumps to Oumuamua, that cigar-shaped mystery that blazed through our solar system in 2017 and sparked 1,000 conspiracy theories. Or maybe 2I/Borisov, the confirmed interstellar comet discovered in 2019 by a Crimean amateur astronomer with a homemade telescope. Those objects came from beyond our solar system, travelled through the space between stars for millions of years, and just happened to pass through our cosmic neighbourhood on their way to somewhere else. 3I/Atlas. Not quite the same story. The comet was discovered on December 28th, 2019 by the Atlas survey system in Hawaii. Atlas stands for Asteroid Terrestrial Impact Last Alert System, which is exactly what it sounds like, a network of telescopes designed to spot things that might hit Earth before they actually do. On that particular night, the automated system flagged a faint smudge moving against the background stars, magnitude 19.6, which means you need a decent telescope just to see it at all. At first, nobody got excited. Comets get discovered all the time. The Minor Planet Center catalogues dozens every year. But as more observations came in and astronomers started calculating the orbit, something unusual emerged. The trajectory showed an eccentricity of 0, 9,999, which in orbital mechanics terms means this thing was barely bound to the sun's gravity at all. One tiny push and it would have been gone forever. The orbit also had an inclination of nearly 45 degrees to the plane of the solar system, coming in from way above the ecliptic where most comets hang out. And its perihelion, the closest point to the sun, was going to be just 0.25 astronomical units. For reference, Mercury orbits at 0.39 AU. This comet was going to get closer to the sun than the innermost planet in our solar system. Dr. Kwanzi Ye from the University of Maryland, one of the first professional astronomers to analyse Atlas, said in a January 2020 paper, "The orbital elements suggest a dynamically new comet, possibly from the Oort cloud, making its first passage through the inner solar system." Translation: this comet had been sitting in deep freeze at the edge of our solar system for 4.5 billion years, and something kicked it inward. Maybe a passing star's gravity, maybe a collision with another icy body. We'll probably never know. But here's where everyone started getting really excited. As Atlas got closer to the sun through February and March 2020, it started brightening. Fast. Way faster than the models predicted. By mid-March, it had jumped from magnitude 19 to magnitude 8 visible to anyone with binoculars. The projection said that by late May 2020, when it made its closest approach to the sun, Atlas could reach magnitude -10. That would make it brighter than Venus, visible in broad daylight, the kind of comet that people would remember for the rest of their lives. Social media went crazy. Astronomers were posting updates daily. News outlets started running stories about the Great Comet of 2,020 inches, arriving just in time to give everyone stuck in pandemic lockdowns something beautiful to look at through their windows. You remember early 2020, right? We could all use something hopeful to stare at. And then, in early April, Atlas started falling apart. The first sign came on April 5th, when the comet's brightness suddenly dropped. Not the gradual dimming you'd expect from changing distance, but a sharp, sudden fade. Within days, telescopes revealed the nucleus had fragmented into at least 4 distinct pieces. By April 11th, amateur images showed the comet had become an elongated smudge rather than a single point of light. Here's the thing: comet fragmentation isn't rare, it happens. Comet Shoemaker-Levy 9 broke into 22 pieces before slamming into Jupiter in 1994, giving us one of the most spectacular astronomical shows in modern history. Comet Linear disintegrated in 2000. Comet Ison, which everyone thought would be the comet of the century, in 2013 evaporated as it swung past the sun. But usually, when a comet fragments, we can track what happens to the pieces. They follow predictable paths. We can measure their brightness, watch them continue to break down or sublimate away. We can see the debris trail stretching behind them, with atlays. That's not exactly what happened. Initial observations from professional telescopes at Gemini North in Hawaii confirmed 4 major fragments, labelled A, B, C, and D. Fragment A was the brightest, probably containing about 40% of the original nucleus mass. The others were smaller, trailing behind in a line like ducklings following their mother. This matched what you'd expect from a comet that had structural weaknesses and couldn't handle the thermal stress of approaching the sun. But then things got weird. By late April, only fragments A and B were still easily visible. C and D had faded beyond detection. The standard explanation was that they'd completely disintegrated, sublimated into gas and dust. Small fragments do that, nothing unusual, except amateur astronomer Carlos Ferreira in Chile, using a 14-inch Schmidt-Cassegrain telescope and a modified DSLR camera, captured something on April 23rd that didn't fit. His images showed fragments A and B right where they should be. But there was also a 5th point of light, moving through the expanding debris field at an angle that didn't match the expected trajectory of any fragment. Ferreira posted his images on astronomy forums with a simple question, anyone else seeing this, within hours. 3 other amateur observers confirmed similar observations. A point source, roughly magnitude 14, travelling at a velocity that suggested it wasn't following the same orbital path as the confirmed fragments. Professional telescopes didn't pick it up. Or if they did, they didn't publish the data. The official catalogues continue to list 4 fragments, with C and D marked as disintegrated by early May. By June 2020, even fragments A and B had faded below naked eye visibility, and scientific interest in Atlas dropped off sharply. The great comet that never was became a footnote in astronomy history, remembered mostly for disappointing everyone during a year that was already disappointing enough. But Carlos Ferreira's images stayed online, and now, 5 years later, in light of what that leaked Hubble data shows, people are going back and looking at those April observations with fresh eyes. Because if there was a companion object travelling alongside Atlas before it fragmented, and if that object survived the breakup while the comet itself fell apart, then what exactly were those amateur astronomers photographing in late April? Was it fragment C or D, somehow surviving longer than expected? Or was it something else entirely? Something that had been hidden in the comet's brightness until the nucleus shattered and revealed what was flying alongside it all along. Let's talk about what the leaked Hubble data actually reveals, because this is where things shift from interesting scientific puzzle to something's not adding up. You need to understand how space telescope observations work. When Hubble points at something, it's not like taking a snapshot with your phone. The Wide Field Camera 3 captures light across multiple wavelengths simultaneously, building up exposure over time to catch incredibly faint objects. Each observation session generates gigabytes of raw data that gets processed through multiple calibration steps before anyone even looks at it. The leaked document shows 4 separate observation windows, March 8th, 11th, 18th, and 22nd, 2020. Each session lasted between 42 and 96 minutes, with multiple exposures stacked to improve signal-to-noise ratio. Standard protocol for observing a comet that's still relatively far from Earth and faint enough that you need every photon you can gather. March 8th. Observation Atlas appears as expected, a slightly fuzzy point source with a developing coma, the cloud of gas and dust that surrounds a comet's nucleus as it warms up approaching the sun. The brightness measurements match ground-based observations from that same period, magnitude approximately 8.5, everything normal. But there, at precisely 0.31 arc-seconds offset from the nucleus, consistently across all 12 exposures taken that night, is a second point source, Fainter, magnitude roughly 13.2 but definitely there. Not a cosmic ray hit, because those show up as single pixel streaks in one exposure and vanish in the next. Not a background star, because it moves with Atlas between exposures. Not a ghost image or internal reflection in the optics, because the brightness and position don't match the patterns those artifacts create. The official analysis notes, written in that standard NASA technical language, classify it as potential fragment or satellite debris. Reasonable first assumption. Comets can have small chunks flying near them, pieces that broke off during previous passes or from impacts with meteoroids. But then look at March 11th. 3 days later, Atlas has moved considerably along its orbit. The companion object's still there, still at 0.31 arc-seconds separation. Still magnitude 13.2. If this was a fragment or debris, orbital mechanics says it should have drifted. Space isn't glue. Objects don't just stick together unless they're gravitationally bound. And Atlas was way too small to hold anything in orbit at 50,000 kilometers distance. March 18th is where the spectroscopic data gets really interesting. Hubble's instruments can break down the light from an object into its component wavelengths, revealing what it's made of. Think of it like a chemical fingerprint. Different materials absorb and reflect different colours of light and characteristic patterns. Atlas's spectrum showed the classic signatures of a comet nucleus, strong absorption lines indicating water ice, signatures of carbon dioxide, carbon monoxide, and various organic compounds. When sunlight hits this stuff and heats it up, these materials sublimate directly from solid to gas, creating the coma and tail that make comets beautiful. The reflectance spectrum matched what you'd expect from a dirty snowball. The standard model for comet composition since Fred Whipple proposed it back in 1950. The companion object's spectrum completely different. First, the albedo. Atlas reflected about 4% of the light hitting it, typical for a carbon-rich, ice-coated surface. The companion reflected 12%. That's 3 times more reflective. You see that kind of albedo in metallic asteroids, or in objects with exposed silicate rock, or in icy surfaces that are extremely smooth and clean. But here's the problem: if it was metallic or rocky, we'd see specific absorption features in the spectrum that match iron, nickel, or silicon compounds. Those features aren't there. If it was clean ice, we'd see the water ice signature. Also absent, what the spectrum shows is almost flat, across the visible and near infrared range. The object reflects light fairly consistently across all wavelengths. That's called a neutral spectrum. And it's rare. Most natural objects in the solar system have distinctive spectral slopes and features based on their composition. The leak document includes a handwritten note next to the spectroscopy plot. Compared to 312 known NEO spectra, no match. Compared to 89 comet nuclei spectra, no match. Compared to catalogue of spacecraft and debris, no match. Someone did their homework. Someone went through every comparison they could think of and came up empty. March 22nd observation is the most revealing, because this is when Atlas was clearly starting to fragment. The nucleus had elongated, stretched by tidal forces and internal stress as volatile ices heated up and created pressure. Professional telescopes would confirm the visible fragmentation within 2 weeks, but Hubble caught it early. The images from March 22nd show Atlas's nucleus distinctly non-spherical, already breaking into what would become the 4 major fragments. The coma had brightened and expanded as fresh ice became exposed to sunlight. This is a comet die-in, essentially coming apart at the seams, and the companion object, still there, still at the same separation, still the same brightness, still showing that flat, featureless spectrum. Now here's what really stands out in the data. Between March 8th and March 22nd, Atlas moved about 0.43 astronomical units along its orbit. That's roughly 64 million kilometres. During that same period, the companion object maintained its relative position to within the measurement precision of the telescope, which for these observations was about 0.02 arcseconds. Do you know how precise that is, maintaining formation spacing of 50,000 kilometres while both objects travel 64 million kilometres through space, threading through the gravitational influences of the Sun, Earth, Venus, Mars, and Jupiter? That's like two airplanes flying side by side from New York to Los Angeles, while staying within 10 feet of each other the entire way, without any radio communication or coordination. Natural objects don't do that. Even binary asteroids, where two rocks orbit their common centre of mass, show measurable variation in separation distance as they move, gravitational perturbations from planets, solar radiation pressure, outgassing from the comet. All of these factors would cause drift. The leaked data includes orbital element calculations for both objects. Atlas had an eccentricity of 0.9999142 with specific values for its semi-major axis, inclination, and argument of perihelion, standard Keplerian orbital mechanics. You can plug those numbers into any astronomy software and predict exactly where Atlas should be at any given time. The companion object's calculated orbital elements are nearly identical, matching to 5 decimal places in some parameters. That's not approximately the same orbit. That's precision formation flying. The last page of the leaked document has a note that wasn't scanned properly. The text is partially cut off, but you can read, "Trajectory analysis suggests active station keeping. No known natural mechanism can explain maintenance of relative position across observed time period. Recommend escalation to," and that's where the page cuts off. Station keeping. That's a term from spacecraft operations. It means actively adjusting your trajectory to stay in a specific position relative to something else. Satellites do it. The International Space Station does it. Comets don't do it. So we're left with a question that has exactly two possible answers. Either the laws of orbital mechanics as we've understood them for the past 400 years since Kepler are wrong, or something was actively controlling its position next to that comet. And honestly, I'm not sure which answer is more unsettling. Before we go any further down this rabbit hole, we need to pump the brakes and ask ourselves an uncomfortable question. Are we seeing what we think we're seeing? Or are we doing what humans have always done? Finding patterns in noise and mistaking the unknown for the impossible? Because here's the thing about space mysteries, we've been wrong before. A lot. Let me take you back to September 20th, 1976. The Soviet Venera 9 spacecraft, orbiting Venus, captured an image that caused a minor panic in certain circles. Right there in the photograph, clear as day, was a bright reflection that didn't match anything in the instrument's field of view. It appeared elongated, metallic-looking, and seemed to be moving independently of the planet's cloud formations. For about 3 weeks, a small group of researchers went quietly wild trying to figure out what it was. Some suggested an unknown atmospheric phenomenon. Others proposed debris from a previous mission. The more imaginative thinkers whispered about something else entirely, something that might be observing our probe the same way we were observing Venus. The truth lens flare. A specific type of internal reflection caused by Venus's incredibly bright cloud tops overwhelming the camera's dynamic range. Once engineers understood the exact geometry of the optics and lighting conditions, they could reproduce the artifact perfectly in testing. Mystery solved. Lesson learned about jumping to conclusions. Or how about 2017 October 19th? Pan-STARRS 1 telescope in Hawaii detected something that changed everything. Object 1/2017 U1 later, named Oumuamua, Hawaiian for Scout. This thing was weird from the start. Its orbit showed it definitely wasn't from our solar system. but the shape elongated, somewhere between 5:1 and 10:1 length to width ratio, like a cigar. Or exactly what you'd design if you wanted to build a spacecraft that could travel between stars efficiently. Then it got weirder. As Oumuamua moved away from the Sun, it accelerated slightly. Not much, just 0.00001 meters per second squared, but enough to deviate from predictions. For a comet, that's normal outgassing creating tiny rocket effect. But Oumuamua showed no coma, no tail, no signs of any outgassing whatsoever. Harvard physicist Avi Loeb published a paper suggesting we should seriously consider the possibility that Oumuamua was artificial. A light sail, maybe, pushed by starlight. The scientific community mostly rolled their eyes. The consensus settled on probably just a weird comet with unusual composition. But the point is, we still don't actually know. Oumuamua is gone now, travelling into deep space, and we'll never get another look. Maybe it was natural and we just don't understand all the ways comets can behave. Maybe Loeb was right. The universe doesn't care about our consensus opinions. Then there's my personal favourite object 2020. So, discovered in September 2020, this thing had an orbit suspiciously similar to Earth's. Its spectrum didn't match any known asteroid type. Its trajectory showed tiny accelerations. Speculation ran wild. Was this a captured asteroid? Something monitoring our planet? NASA tracked it carefully. In December 2020, they announced what it actually was, the Centaur upper stage from the Surveyor 2 mission. Launched in 1966. It had been floating around in solar orbit for 54 years before Earth's gravity temporarily captured it again. We'd literally been observing a piece of 1960s American rocket hardware and didn't recognize it. These examples matter because they establish a pattern. Most of the time, when we see something we don't understand in space, it turns out to have natural explanation. The universe is strange enough without needing to invoke anything extraordinary. So what are the most common mistakes people make when analysing unusual observations? First is confirmation bias. Once you decide you're looking at something anomalous, your brain starts filtering data to support that conclusion. You notice every detail that seems unusual and unconsciously dismiss the details that suggest normal behaviour. Scientists are just as susceptible to this as anyone else. Second is resolution limits. Hubble is incredible, but it's not magic. At the distances we're talking about, objects smaller than a few kilometres might appear as single pixels. That means we're trying to extract information from extremely limited data. Imagine trying to identify someone's face from a photograph where their entire head is 4 pixels. You might convince yourself you see specific features, but you're mostly seeing what you expect to see. Third is misunderstanding orbital mechanics. Space doesn't work like Earth. Objects don't need engines to maintain orbits. They don't slow down from friction. Weird trajectories that seem impossible often turn out to be perfectly normal once you account for all gravitational influences and actually do the math properly. I've seen people claim objects are violating physics because they don't understand how solar radiation pressure affects small particles, or because they forget that planets are constantly moving and their gravitational influences change. Orbital mechanics is genuinely difficult. There's a reason aerospace engineers spend years studying it. So applying all that skepticism to the Atlas companion object, what natural explanation should we eliminate first binary comet systems exist? 67P/Churyumov-Gerasimenko. The comet Issei's Rosetta mission visited turned out to be 2 distinct lobes stuck together. If Atlas had a chunk gravitationally bound to it, that could explain a companion, except the separation distance doesn't work. Atlas's nucleus was probably 5 to 10 kilometers across with a mass around 1 trillion kilograms. Tops. To hold an object in orbit at 50,000 kilometers distance, you'd need way more mass. The math doesn't close. Binary comet ruled out. Trojan configuration Earth has Trojan asteroids at its L4 and L5 Lagrange points. Could Atlas have temporarily captured something there? Theoretically possible. But those points are only stable with a significant mass ratio, like Earth and the Sun. A tiny comet doesn't create stable Lagrange points that could trap anything for more than a few weeks. We observed the companion for at least 14 days across different orbital positions. Trojan configuration also ruled out debris from an ancient collision. Maybe Atlas collided with something years ago, creating fragments in similar orbits. We see this with asteroid families where hundreds of smaller rocks share nearly identical orbits because they came from the same shattered parent body. But spectroscopy kills this idea. Atlas showed typical comet composition. The companion showed that weird neutral spectrum with higher albedo. If they came from the same parent body, they should have the same composition. You don't get metallic-looking fragments from an icy comet collision. Collision debris doesn't fit instrumental artifact. This is actually the most reasonable natural explanation, and it's probably what most astronomers would default to, except the leaked data includes those handwritten notes about checking calibration 6 times and comparing against known artifact patterns. Whoever analysed this data knew what ghost images look like and explicitly ruled those out. Plus, if Hubble creates a ghost image at 0.31 arcseconds offset under certain conditions, it should do that every time. But other comet observations from the same period, using the same instrument, don't show these secondary signatures, just Atlas, which brings us back to the uncomfortable conclusion. If we've eliminated the natural explanations, if we've accounted for observational errors and instrumental quirks, then we're left with something unprecedented. That doesn't automatically mean artificial. It doesn't mean aliens. It means we're looking at a phenomenon we don't have a good explanation for yet. And that's actually the most exciting place to be in science. That's where discoveries happen. But it also means we need better data, more observations, different instruments. And that's where this story takes a frustrating turn, because the one thing we need most is the one thing we're not getting transparency from the people who have access to the information. All right, let's do something that might seem counterintuitive. Let's actively try to prove ourselves wrong. Let's take every possible natural explanation for the Atlas companion and push it to its absolute limits. Because if there's one thing science has taught us, it's that nature is far more creative than we give it credit for. So what if this entire mystery has a perfectly natural explanation that we just haven't thought of yet? Start with the most basic question: what holds things together in space? Gravity. Right, it's the weakest of the 4 fundamental forces, but over large distances, it's the only one that matters. For 2 objects to orbit each other, you need enough gravitational attraction to overcome their tendency to just fly off in straight lines. But a comet, we're talking about a dirty snowball maybe 10 kilometers across. Let me put that in perspective. If you scaled Earth down to the size of a basketball, Atlas would be smaller than a grain of sand. I actually did the math, using Newton's law of universal gravitation. If Atlas had a mass of about 10 trillion kilograms, which is generous, and the companion had a mass of maybe 1 million kilograms, the gravitational force between them at 50,000 kilometers separation would be about 0.000004 newtons. That's roughly the force you'd feel if a mosquito landed on your hand, except in space. Between 2 objects each travelling at tens of kilometers per second, that force is nowhere near strong enough to keep 2 objects in stable formation over 2 weeks, let alone through the violent fragmentation that tore Atlas apart. So gravitational binding off the table. What about electromagnetic forces? Comets can develop substantial electric charges as they interact with the solar wind. When charged particles from the sun hit the comet's coma, they can create charge separation. building up voltage differences. But to hold two objects in formation electromagnetically, you'd need them to have opposite charges and be close enough that the force overcomes the sun's gravity trying to separate them. At 50,000 kilometers, the electromagnetic force would be even weaker than gravity. And charged objects in the solar wind don't maintain stable positions. They get buffeted around by variations in solar wind speed and density, so electromagnetic binding also doesn't work. What if we're thinking about this wrong entirely? What if the companion isn't being held in place by Atlas, but rather both objects are following the same trajectory because they form together? Think about it like two leaves falling from a tree. If they start from the same branch at the same moment, they might fall along very similar paths for a while, even though they're not connected. Could Atlas and its companion be like that? Maybe they're both chunks from a larger parent body that broke apart years ago, and they've been following nearly identical orbits ever since. This is actually the most plausible natural explanation. We know comet splitting happens. Comet Schwarzmann-Wachmann 3 fragmented in 1995 and by 2006 had broken into dozens of pieces, all following similar but slightly different orbits. But here's the critical detail: those fragments drift apart over time. Orbital mechanics is exquisitely sensitive to initial conditions, even tiny differences in velocity, like a few centimeters per second, accumulate over weeks into separations of thousands of kilometers. The leaked Hubble data shows observations span in 14 days. During that time, Atlas travelled 64 million kilometers. If the companion was truly independent, following its own orbit that just happened to be similar, we should see measurable drift in their separation. Perturbations from planetary gravity, solar radiation pressure, and the comet's own outgassing would cause their paths to diverge. Yet the separation remained constant within the measurement precision of the telescope. That's not approximately the same orbit. That's synchronized motion. Have you ever watched those videos of starling murmurations? Thousands of birds moving in perfect coordination. Each bird follows simple rules based on its neighbours. From those individual behaviours, complex group patterns emerge. Could something like that explain the Atlas companion, some natural feedback mechanism that causes the objects to maintain formation? The problem is, birds have eyes and brains and can adjust their flight in real time. Rocks in space don't have sensors. They don't have thrusters. They can't detect their position relative to a nearby object and make course corrections. They just follow the trajectories that physics dictates. Unless there's a physical mechanism we don't understand, which would be new physics, which would be Nobel Prize territory, which is possible, but we should probably exhaust conventional explanations first. What about tidal forces? When an object passes close to a massive body, gravity on the near side is stronger than on the far side, creating stress. This is how comet Shoemaker-Levy 9 got torn into pieces before hitting Jupiter. The math says no. Tidal forces cause stretching along the line connecting two massive bodies. The companion object was offset perpendicular to the Sun-comet axis, not aligned with it. Tidal forces can't explain perpendicular formation flying. What about resonance phenomena? In orbital mechanics, resonance occurs when objects have orbital periods that are simple integer ratios. Neptune and Pluto are in a 3-2 resonance. These can be surprisingly stable and cause objects to maintain specific geometric relationships. Could Atlas and its companion be in some kind of resonance? This uses known physics in a creative way, but resonances work over multiple orbital periods. They're statistical patterns that emerge from gravitational interactions repeated thousands or millions of times. Atlas was making its first and only close approach to the Sun. There wasn't time for resonance patterns to establish. And tiny comets don't have the gravitational strength to create stable resonances anyway. Here's where we arrive at an uncomfortable place. We've pushed natural explanations as far as they'll go. We've tried to be generous with the physics, creative with the possibilities, and everything comes back to the same conclusion, maintaining precise formation over 64 million kilometers of travel through a fragmentation event without measurable drift requires something that natural processes as we understand them simply don't provide. That leaves us with two options. Either our understanding of physics is incomplete in ways we haven't realized, or something was actively controlling its trajectory. The first option means we're on the verge of discovering new natural phenomena. The second option means we're looking at technology. And if it's technology, then the question becomes unavoidable. Whose technology? Because there are exactly three possibilities, and none of them are comfortable to think about. But we need to think about them anyway, which is exactly where this investigation leads us next. Here's what most people don't understand about NASA. It's not a monolithic organization with a single unified approach to sharing information. It's a massive bureaucracy with multiple centers, competing priorities, and layers upon layers of oversight. And when something doesn't fit into the established boxes, when data arrives that challenges existing models or raises uncomfortable questions, there's a protocol for how that information gets handled. That protocol is what we need to understand if we want to make sense of why the Atlas companion data stayed buried for 5 years. Let me show you how NASA typically handles anomalies by looking at 3 very different case studies. First, the Mars face. In 1976, Viking 1 orbiter captured an image of a mesa in the Cydonia region that, due to lighting and shadow, looked remarkably like a human face staring up from the Martian surface. The image leaked to the press before NASA could provide context. Tabloids went wild. Ancient Martian civilization discovered, headlines like that. NASA's response: immediate transparency. They released the full image set, explained the lighting conditions, and promised to rephotograph the site with better cameras when possible. In 2001, Mars Global Surveyor did exactly that, capturing high-resolution images that clearly showed the face was just an ordinary mesa. No cover-up, no suppression, just patient science and open communication second-cased the WOW signal from 1977. Ohio State's Big Ear radio telescope detected a 72-second burst of narrowband radio emission that perfectly matched what SETI researchers expected from an artificial extraterrestrial source. The astronomer who discovered it literally wrote "WOW" in the margins of the printout. What happened next? The data went public immediately. SETI made no attempt to classify or suppress it. They've been trying to detect the signal again for 48 years, without success. The consensus now is it was probably a rare natural phenomenon, maybe involving a comet that happened to be in the beam at the right moment. But the point is instant transparency. No embargo, no classification. Third case. More recent phosphine on Venus. In September 2020, astronomers announced detection of phosphine gas in Venus's atmosphere. On Earth, phosphine is almost exclusively produced by biological processes or industrial chemistry. Finding it on Venus raised the tantalizing possibility of aerial microbial life. NASA's response cautious. They waited for peer review. They funded follow-up observations. They didn't immediately call a press conference claiming we'd found life on Venus. And good thing too, because subsequent analysis suggested the detection might have been contaminated by sulfur dioxide signals. The phosphine claim is still controversial. But here's the key: NASA never classified the data, never tried to suppress it. They just exercised appropriate scientific caution while the debate played out in public. So we have 3 examples of NASA dealing with anomalous or potentially revolutionary observations. In 2 cases, immediate transparency. In 1 case, scientific caution but still public discourse. Standard operating procedure for an agency whose charter literally requires it to provide for the widest practicable and appropriate dissemination of information. Now compare that to Atlas. 5 years of silence. Data classified under ITAR, the International Traffic in Arms Regulations. That's not scientific caution. That's active suppression using legal frameworks designed for weapon systems and military technology. Why the different approach? I reached out to 3 former NASA contractors who agreed to speak on background, meaning I can share what they said but not their names. These are people who worked in data analysis and mission planning during overlapping periods. Their accounts corroborate each other in interesting ways. Here's what one of them told me. When observational data doesn't fit the expected model, there's a 3-tier review process. First, the science team examines it for instrumental errors or calibration issues. If they can't explain it that way, it goes to the program manager level. That's where decisions get made about whether this is publishable science or whether it needs additional review. Most things that seem anomalous get resolved at Tier 1 or 2. But occasionally, they continued, something makes it to Tier 3. That's when it crosses from science into policy. When the implications of releasing the data might affect national security considerations, international relations, or public perception in ways that go beyond pure scientific interest. At that point, people outside NASA get involved. DoD sometimes, intelligence community. It becomes less about what the data shows and more about how releasing it might be perceived or used. Another former contractor put it more bluntly, look, NASA is funded by Congress. Congress responds to public opinion and political pressure. If you're a program manager and you've got data that might spawn conspiracy theories, might get misinterpreted, might lead to congressional hearings where your budget gets questioned, you're going to be very careful about how and when that information becomes public. It's not a conspiracy, it's bureaucratic self-preservation. But here's what doesn't add up. NASA has dealt with weird data before without resorting to ITAR classification. The Mars face could have spawned conspiracy theories. They released it anyway and dealt with the fallout. Oumuamua's unexplained acceleration could have led to wild speculation. The data stayed public and scientists debated it openly. What made the Atlas companion different? The timing offers a clue. March 2020. Do you remember what else was happening in March 2020? The COVID-19 pandemic was exploding globally. The WHO declared it a pandemic on March 11th. By March 22nd, the date of the last ATLAS observation, half the United States was under lockdown orders. NASA itself was transitioning to remote operations. The news cycle was dominated 24/7 by infection rates, death tolls, and economic collapse. Maybe, in that chaos, someone made a calculation. Maybe they looked at this anomalous data, recognized it would raise questions they couldn't immediately answer, and decided that March 2020 was exactly the wrong time to add mysterious object accompanying comet to the list of things people were worried about. And maybe that decision, made in the moment for what seemed like reasonable crisis management, became harder to reverse as time went on. Because once you've classified something, once you've created an official position that this data requires special handling, admitting you were wrong means admitting you suppressed scientific information for non-scientific reasons. There's precedent for this kind of decision calculus. In 2021, the Pentagon released its UAP report, acknowledging 144 incidents of unidentified aerial phenomena observed by military personnel. They admitted they couldn't explain most of them. The report's release came after years of leaked videos and mounting public pressure. What changed? Not the data. The data had been sitting in classified files for years. What changed was the political calculation. Someone decided that transparency, even about things they couldn't explain, was less damaging than continued secrecy fueling speculation. The ATLAS companion data might be stuck in that same calculation. 5 years ago, in the chaos of a pandemic, classification seemed prudent. Now, with leaked documents circulating and amateur astronomers asking questions, that same classification looks increasingly like a cover-up, which creates exactly the kind of conspiracy theory spiral that classification was supposed to prevent. So here we are, an agency that usually prioritizes transparency, bound by its own earlier decision to suppress data that might not have warranted suppression in the first place, unable to release the information without explaining why it was classified, unable to keep it classified now that pieces have leaked. It's not a conspiracy. It's a bureaucracy that made a questionable call under pressure and now can't figure out how to walk it back without making things worse. Which might be the most frustrating explanation of all, because it means we're not dealing with hidden truths. We're dealing with institutional paralysis. But while NASA sits frozen in its own procedural quicksand, the data exists, and data doesn't care about organizational politics. Numbers are numbers. Trajectories are trajectories. And independent analysts with the leaked documents are doing what NASA should have done 5 years ago, actually analysing what the observations tell us. While NASA was sitting on classified data, and bureaucrats were arguing about disclosure protocols, something interesting was happening in the corners of the internet where people actually know how to read orbital mechanics equations. Remember those 1,847 downloads of the leaked PDF? Turns out a significant number of those people weren't conspiracy theorists or casual space enthusiasts. They were astronomers, physicists, and aerospace engineers who saw raw data and immediately thought, I can work with this. Within 72 hours of the leak, 3 independent analysis teams had formed, completely separate from each other, working in different countries. One group centered around retired JPL engineers in California, another formed at University Astronomy Department in Germany. The third was a loose collaboration of amateur astronomers and data scientists spread across 5 continents, coordinating through encrypted forums, and all 3 groups reached essentially the same conclusions, which is either a remarkable coincidence or a sign that the data is telling us something real. Let's walk through what they found, starting with the most straightforward analysis, the albedo problem. Albedo is the fraction of sunlight an object reflects. Fresh snow has an albedo around 0.8 to 0.9, meaning it reflects 80 to 90% of incoming light. That's why it's so bright. Charcoal, on the other hand, has an albedo around 0.04, absorbing most light and reflecting very little. Comet nuclei typically fall into that dark carbon-rich range. They're basically dirty snowballs covered in a layer of dust and organic compounds that have been cooked by radiation for billions of years. The leaked Hubble data includes photometry measurements across multiple wavelengths. That's fancy talk for measuring how bright something appears in different colours of light. From those measurements, you can calculate albedo. Atlas's nucleus, albedo 0.04, exactly what you'd expect. The companion object, albedo 0.12, that's 3 times more reflective. The German team ran the numbers through a comparative database of every spectral type we've catalogued in the solar system, metallic asteroids like 16 Psyche. Those can hit albedos of 0.12, but they show distinctive absorption features from iron and nickel, not present in the companion spectrum. Icy moons like Europa high albedo, but strong water ice signatures, also absent. What shows that kind of neutral, featureless spectrum with moderate albedo? Very few natural objects. And the ones that do are all explained by specific surface processes we can identify. One of the JPL engineers, I'll call him Richard, ran a contamination analysis. Could the brightness and spectrum of the companion be explained by the comet's coma contaminating the measurements when a comet is actively outgassing? The dust and gas around it can scatter light in ways that might create false signatures. Richard's analysis showed that at 50,000 kilometers separation, Atlas's coma would have been too diffuse to significantly affect measurements of a separate object. The density drops off exponentially with distance. By the time you're 10,000 kilometers out, you're basically looking through near vacuum with occasional dust grains. The companion's brightness and spectrum are its own, not reflected contamination from Atlas. Then there's the thermal analysis. This is where things get really interesting. When sunlight hits a comet, it heats up. The ices sublimate, turning directly from solid to gas. This process absorbs energy, cooling the nucleus, but it also creates a detectable thermal signature. Infrared telescopes can measure this heat and use it to determine composition, size, and activity level. Atlas showed exactly what you'd expect: a thermal signature consistent with water ice sublimation, with temperatures varying based on solar distance and rotation. The comet was doing comet things. The companion object. The leaked data includes limited infrared observations from March 18th. Those measurements show no thermal excess, no heat signature beyond what you'd expect from passive solar heating of inert material. Whatever this object was made of, it wasn't sublimating, it wasn't outgassing, it was just sitting there, absorbing and re-radiating solar energy like a rock. Which would be fine if it was a rocky asteroid, except the trajectory analysis shows it wasn't following a typical asteroid orbit. This is where the math gets technical, but stay with me because this is the part that's genuinely inexplicable. Objects in space follow trajectories determined by gravity. If you know the position and velocity of an object at one moment, and you know the gravitational fields it's moving through, you can predict exactly where it will be at any future time. This is called Keplerian orbital mechanics, and it's been tested to absurd precision for 400 years. The International Amateur Group ran the companion object's position data through multiple orbital determination software packages: SDK, GMAT, ORAKIT. These are professional-grade tools used by actual space agencies to plan missions. They plugged in the March 8th position and velocity, then calculated where the object should have been on March 11th, 18th, and 22nd based purely on the sun's gravity. The predicted positions didn't match the observed positions. The differences were small, just a few arcseconds, but they were consistent and directional. The companion was systematically offset from where pure gravitational dynamics said it should be, and the direction of those offsets suggested a small but persistent acceleration in the direction tangent to its orbit. How small? About 0.03 meters per second squared. That's roughly 3% of the acceleration you feel from gravity on Earth. Tiny, but when sustained over days, it adds up. One member of the group, a doctoral student in astrodynamics, posted this comparison. Oumuamua showed a non-gravitational acceleration of about 0.00001 meters per second squared, and that was enough to cause a major scientific controversy. This object is showing an acceleration 3000 times larger. Could it be measurement error? They checked. Hubble's positional accuracy for point sources is about 0.01 arcseconds. The offsets were larger than the error bars. Could it be software glitches? They used 3 independent programs and got the same results. Could it be that they didn't account for all gravitational influences properly? They included perturbations from every planet, major asteroid, even relativistic corrections, still didn't close the gap. There's a term in astrodynamics for when your observed trajectory doesn't match your predicted trajectory residuals. They're the leftover differences after you've accounted for everything you understand. Small residuals are normal, they indicate measurement uncertainty or minor effects you didn't model. Large, systematic residuals mean something significant is happening that your model doesn't include. The companion object had large, systematic residuals pointing in the direction of its motion, as if something was pushing it forward along its orbit. Station keeping, that leaked note called it. The math backs up that description. Richard from JPL put it most clearly in his public analysis. I've worked on trajectory design for Mars orbiters, lunar landers, and interplanetary missions for 23 years. I know what natural trajectories look like. I know what thrusters look like. This looks like thrusters. But it gets even stranger. Between March 18th and 22nd, when Atlas was visibly fragmenting, the companion object's trajectory showed no change in its acceleration profile. No reaction to debris, no deflection from impacts. Just smooth, consistent motion like it was following a predetermined path, programmed before the comet even started breaking apart. Think about what that implies. Either this object knew the comet was going to fragment and compensated in advance, or it was following a trajectory completely independent of Atlas and just happened to be travelling alongside it. The first option suggests impossible foreknowledge. The second option raises the question if it wasn't gravitationally bound to Atlas, wasn't affected by Atlas's breakup, and maintained precise formation anyway, then why was it there? What was it doing? These aren't rhetorical questions. These are the actual questions that independent researchers are asking in published analyses. And the fact that NASA won't engage with these questions, won't release their higher resolution data, won't even acknowledge that the leaked information is legitimate, that silence is starting to look less like bureaucratic caution and more like intentional avoidance. The math doesn't lie. Numbers don't have agendas. And the numbers are telling us that something maintained a controlled trajectory next to a fragmenting comet for at least 2 weeks in March 2020. Whether that something was natural or artificial is the question. But that it was controlled, the math is pretty clear about that. Alright, we've looked at the data, we've examined the natural explanations and found them wanting. We've seen the independent analyses all pointing toward the same uncomfortable conclusion: something was maintaining a controlled trajectory alongside Atlas. Now comes the hard part. We need to actually propose explanations for what that something might be. Science works by generating hypotheses and testing them against evidence. Some are conservative, requiring only small adjustments to what we know. Others are radical, demanding we rethink fundamental assumptions. The key is being honest about the probability of each. So let's rank 5 competing hypotheses by scientific plausibility, starting with the most likely and working toward the edges of possibility. Hypothesis 1. Observational artifact, 90% probability. Despite all the analysis, despite the independent verification, the most likely explanation is still that we're being fooled by some combination of instrumental quirks, data processing errors, or observational circumstances that create the appearance of a companion object when nothing unusual is actually there. Consider Comet 17P/Holmes. In October 2007, this normally faint comet suddenly brightened by a factor of 500,000. Initial observations made it look like the nucleus had split into multiple pieces. Amateur astronomers posted images showing what appeared to be several distinct objects. Professional follow-up revealed the truth: the comet had experienced a massive outburst, ejecting dust that temporarily created multiple brightness peaks in the coma. The multiple nuclei were optical illusions created by uneven dust distribution. Once astronomers understood the geometry, the mystery resolved into perfectly normal comet behavior. Could something similar explain the Atlas companion? Maybe the comet's outgassing created a dense pocket of dust that reflected light in ways that mimicked a separate object. Maybe Hubble's instruments, pushed to their limits, produced ghost images under specific conditions. The problem is that the leaked notes explicitly state the analysts checked for these scenarios and ruled them out. But mistakes happen. Confirmation bias happens. Someone convinced they're seeing something real might unconsciously dismiss contradictory evidence. Until independent astronomers can reproduce the observations, or until NASA releases enough data for broader examination, observational artifact remains the statistically most probable answer. Even if it doesn't feel satisfying. Hypothesis 2. Natural but unprecedented. 8% probability. Maybe we're looking at a real physical phenomenon, just one we've never encountered before because the right conditions are incredibly rare. Think about Mars's moons, Phobos and Deimos. The leading theory is that Mars captured them, they were asteroids that got too close. But capture is really hard. An object approaching a planet is usually moving too fast. It just swings past and keeps going. For capture to work, something needs to slow it down at exactly the right moment. Aerodynamic drag through the atmosphere can do this. Tidal forces can deform weak objects, converting kinetic energy to heat and slowing them down. Could something analogous have happened with Atlas? Maybe when the comet passed through the inner solar system on a previous orbit? It encountered unusual circumstances that resulted in it acquiring a companion through a process we don't have a name for yet. And maybe that companion, through some mechanism involving the comet's coma, solar radiation pressure, magnetic fields, and a dozen other factors, ended up in a quasi-stable configuration that looks like station keeping but is actually an emergent property of complex interactions we don't have equations for. This would be like discovering a new type of chemical bond. Unprecedented. But still natural physics. Just physics we haven't fully mapped out. The challenge is that physics tends to be universal. If this process can happen, it should happen more than once. We should see other examples, even if rare, and we don't. In 70 years of careful solar system observation, Atlas would be the only documented case. That doesn't make it impossible, but it makes it unlikely. Hypothesis 3. Human-made object 1.5%. Probability. What if the companion is something we put up there and forgot about? Since Sputnik in 1957, humans have launched over 15,000 objects into orbit or beyond. Most attract, some aren't. Occasionally, decades-old hardware shows up in unexpected places. Remember Object 2020. So, turning out to be a 1966 rocket stage. Could the Atlas companion be lost spacecraft or space junk that happened to be in the right place at the right time? The trajectory analysis makes this difficult. For a human-made object to match Atlas's orbit so precisely, it would need to have been launched on a very specific mission. And we have records of those missions. Every deep space probe, every planetary mission, every trajectory has been catalogued. The International Amateur Group cross-referenced the companion's calculated orbit against every known deep space mission from 1960 to 2020. Nothing matched. Not even close. You could argue for secret military spacecraft. But why would any military launch something on an orbit that accomplishes nothing except flying next to a random comet, unless it wasn't intentional? Unless some classified spacecraft ended up on an unexpected trajectory due to malfunction, and rather than admit the error, the relevant agency quietly let it drift away and hoped nobody noticed. That's barely possible, but the spectrum still doesn't match manufactured materials we use for spacecraft. And the lack of thermal signature suggests no electronics, no power systems, no active components. Just inert mass, which makes the trajectory control even harder to explain. Hypothesis 4. Extrasolar probe 0.4% probability. Now we're into territory that makes most scientists uncomfortable. But let's be intellectually honest. If we're considering hypotheses, we can't exclude this one just because it challenges our assumptions. The companion shows characteristics consistent with an observation probe small, low thermal signature, maintaining formation with a target. If you wanted to study a comet up close, especially one making a rare dive toward the Sun, this is exactly what you'd do. Send something to fly alongside it and collect data. Avi Loeb proposed this kind of explanation for Oumuamua's anomalous acceleration. A light sail pushed by solar radiation could show exactly the trajectory deviations observed. He caught endless criticism, but his math was sound. For the Atlas companion, you'd need different propulsion. Light sails accelerate away from the Sun, not along orbital paths, but electric propulsion, like ion drives, could maintain formation while consuming minimal fuel and producing almost no detectable exhaust. The immediate counter-argument: but why would aliens be interested in our random comet? Maybe because it's not random to them. Maybe they've been cataloguing comets across this region of the galaxy for centuries. Maybe Atlas's particular trajectory flags something in their detection systems worth investigating. We're not talking about aliens specifically interested in us. We're talking about probes doing automated survey work throughout the galaxy. And one happened to pass through our neighbourhood when Atlas did. Improbable, absolutely. Impossible, no. And the math doesn't discriminate. An object showing controlled trajectory is showing controlled trajectory, regardless of who or what is doing the controlling. Hypothesis. 5. Natural phenomenon. We don't understand yet. 0.1% probability. This is the wild card, the unknown unknowns category. Dark matter was proposed in 1933 to explain galaxy rotation curves. For decades, it was fringe. Now it's scientific consensus. We still don't know what dark matter particles are, but we're confident something accounts for 85% of the universe's mass. Neutron stars were predicted theoretically in the 1930s, but considered borderline speculative until detected in 1967. Same with black holes. Same with gravitational waves. History's full of phenomena that seemed impossible right until we found them. Maybe there's some interaction between solar magnetic fields and cometary plasma that creates stable equilibrium points we've never modelled. Maybe there's a class of small objects with unusual composition that exhibits emergent behaviour under specific conditions. Maybe the universe has tricks we haven't imagined yet. This hypothesis gets the lowest probability not because it's least plausible, but because it's least specific. It's essentially saying something else we haven't thought of. That's not falsifiable. It's not testable. But it's also the most scientifically exciting possibility, because it means there's new physics to discover. Not aliens, not conspiracy, just nature being weirder than our current models predict. So where does that leave us? 5 hypotheses, ranging from 90% to 0.1% probability. The math says artifact. The conservative approach says artifact. The burden of proof demands artifact be disproven before entertaining wilder possibilities. But the data, that stubborn leaked data with its station-keeping notation and unexplained accelerations, keeps whispering, what if it's not artifact? What if the 10% scenario is actually true? Because if it is, we need to think seriously about what happens when definitive proof emerges. And that question isn't about science anymore. It's about us. Let's play a game. Not a fun game, but a necessary one. Let's imagine 3 different endings to this story and walk through what each one means for us, for science, and for how we understand our place in the universe. Because here's what nobody talks about when we're obsessing over leaked PDFs and orbital mechanics. The answer to what was that object matters far less than what we do with that answer once we have it. Scenario A, it's nothing. The most likely outcome, NASA finally releases their full dataset. Independent teams analyse it with fresh eyes and better tools. Someone finds the flaw. Maybe there was a software glitch in the orbital calculation. Maybe the spectroscopy was contaminated by scattered light from Mars. Maybe the whole thing was exactly what the initial classification suggested, an instrumental artifact that looked interesting but ultimately meant nothing. The leaked document gets relegated to the same digital dustbin as the Mars face and the wow signal. Case closed. Universe remains exactly as boring as we thought. But here's the problem with this scenario damage to public trust. For 5 years, NASA sat on data that might have been important. They classified it under weapons regulations. They refused to comment when it leaked. And then, after all that secrecy, it turns out to be nothing. Think about how that plays. Every conspiracy theorist who ever accused NASA of hiding information gets validation. Not because NASA was actually hiding aliens, but because NASA demonstrated they're willing to suppress scientific data for bureaucratic reasons. The next time NASA says we're being transparent, why should anyone believe them? There's historical precedent. After SETI's numerous false alarms in the 1970s and 80s, Congress cut their funding. Not because the science was bad, but because politicians got tired of explaining to constituents why taxpayer money was being spent on searches that kept coming up empty. SETI had to survive on private donations for decades. If the 8-less companion turns out to be nothing, expect similar consequences: budget cuts to planetary observation programs, reduced support for anomaly investigation, a cultural shift within NASA toward playing it safe, only publishing results that fit established models, avoiding anything that might generate controversy. Science thrives on investigating the unexplained, but science also requires funding, and funding requires public and political support. Erode that support enough times, and you strangle the curiosity that drives discovery in the first place. Scenario B, it's something unprecedented, but natural. Now imagine the opposite. NASA releases the data, and it holds up. The companion object is real. The trajectory, anomalies are real. But after months of intensive study involving the world's best astrophysicists, someone figures it out. Maybe there's a previously unknown interaction between solar wind and cometary plasma that can create stable pockets of concentrated material. Maybe we discover a new class of objects, neither quite comet nor quite asteroid, with properties we'd never anticipated. Maybe the solution requires adding new terms to our orbital mechanics equations, refining models that have worked perfectly well for 4 centuries but turn out to be incomplete at certain scales. This would be huge. Not Nobel Prize huge, but definitely career-making, textbook rewriting huge. It's the kind of discovery that expands human knowledge without overturning it. We'd understand the universe a little better. Students 50 years from now would learn about Atlas-type companions, the same way they learn about Trojan asteroids or Kuiper belt objects. The scientific renaissance that follows would be incredible. Funding agencies would pour money into searches for similar objects. Every comet observation would include protocols for detecting companions. We'd develop new instruments specifically designed to spot these phenomena. Amateur astronomers would have a new category of object to hunt for, and crucially, it would validate the scientific method. Someone observed something weird, collected data, proposed hypotheses, and through rigorous testing we figured out the truth. That's how science is supposed to work. That's the story we tell ourselves about progress. But there's a darker side to this scenario too. If the discovery requires admitting that our models were incomplete, how many other assumptions are we making that might also be wrong? How much of what we know about the solar system is actually just our best guess based on limited observations? That uncertainty can be paralyzing, or it can be liberating. Depends on whether you see gaps in knowledge as problems to fix or opportunities to explore. Scenario C, something artificial. Now, the uncomfortable one, the scenario that most scientists refuse to seriously engage with. Not because the evidence rules it out, but because the implications are too large to process. Let's say conclusive proof emerges that the Atlas companion was artificial, not human-made, not natural. Something designed and built by an intelligence that isn't us. First question everyone asks, why didn't it make contact? Maybe because it wasn't interested in us. Maybe because it was fully autonomous, following programming written thousands of years ago. Maybe because whatever sent it doesn't think about communication the way we do. Remember, we're not talking about an Independence Day scenario where alien ships appear over major cities demanding to speak to our leaders. We're talking about a small object that quietly accompanied a comet for a few weeks and then continued on its way. No interaction, no message, just passive observation. If that, here's what happens next. And this is based on actual protocols that exist in draft form at various institutions. The International Academy of Astronautics has a SETI post-detection protocol that was established after the WOW signal. It outlines procedures for verification, notification of authorities, and public disclosure. But those protocols were written assuming detection of a radio signal, not discovery of physical hardware. The procedures get murky. Who represents humanity? The United Nations NASA, the country that made the discovery. There's no clear answer because nobody seriously expected to need one. Meanwhile, panic sets in. Not necessarily widespread public panic, but institutional panic. Defense departments want to know if there are more of these objects and whether they pose a threat. Intelligence agencies want to know if this represents surveillance. Religious institutions grapple with theological implications. Philosophers dust off their first contact scenarios and realize most of them were embarrassingly Earth-centric. And here's the truly fascinating part. Nothing changes immediately. The sun still rises. People still go to work. The economy doesn't collapse, because the universe we thought we knew and the universe we actually live in turn out to be slightly different, but our daily lives remain mostly the same. Except for one thing. The Fermi paradox gets answered. Where is everybody? They're here? They've been here? Maybe they've been observing for centuries and we only just now developed the tools to notice them. That realization that we might not be alone and might never have been alone reshapes everything. Not immediately, not dramatically, but gradually, fundamentally. The way heliocentrism reshaped everything after Copernicus. The way evolution reshaped everything after Darwin. We'd still be us. We still have our problems, our politics, our daily struggles. But we'd be us in a universe where we're definitively not unique, where intelligence and technology arose at least twice, where the galaxy might be filled with observers cataloguing everything, including us. Some people would find that terrifying. Others would find it comforting. Many would find it anticlimactic. After all, if aliens have been quietly watching us this whole time and haven't done anything, maybe they're as boring as we feared the universe was. But for anyone who's ever looked up at the stars and wondered, are we alone? The answer would finally, definitively, be no. And that's worth something. That might even be worth 5 years of bureaucratic suppression and leaked PDFs and amateur astronomers arguing on forums at 3 a.m. The question isn't whether we can handle the truth. History suggests we'll handle whatever truth emerges the same way we handle everything else, with a mixture of denial, acceptance, adaptation, and endless arguing about what it means. The real question is whether we'll get the chance to handle it. Whether the data will be released, whether transparency will win over secrecy, whether bureaucratic inertia can be overcome by simple human curiosity demanding answers. And that brings us to the final piece of this puzzle. Because while institutions debate and scientists analyze, there's something everyone seems to forget. The data is already out there. The tools are available. The sky is accessible to anyone with a telescope and patience. This isn't NASA's mystery to control anymore. It's ours, all of ours. and maybe it always should have been. So here we are, 10 parts into a story that started with a leaked PDF and ends with us staring at a question mark the size of the solar system. NASA isn't talking, the data is contested. The explanations range from nothing to see here to everything we thought we knew is wrong. And you're probably thinking, okay, interesting story, but what am I supposed to do with this information? Here's the thing. Most science documentaries don't tell you you're not just an audience. You're not a passive consumer waiting for experts to hand down answers from on high. The tools to investigate this mystery yourself, the same tools professional astronomers use, are available to you right now. And the community doing the most interesting work on cases like this, it's not coming from prestigious universities with billion-dollar budgets. It's coming from people working day jobs who spend their nights pointing telescopes at the sky, because they can't shake the feeling that there's something up there worth finding. Let me show you exactly how you can become part of this investigation instead of just hearing about it. First, access the data yourself. Everything NASA collects eventually becomes public. Not immediately, not always in user-friendly formats, but it's there. The Planetary Data System archives decades of spacecraft observations. The Minor Planets Center catalogues every asteroid and comet discovery, with full orbital parameters. The Space Telescope Science Institute hosts every Hubble observation ever taken, including the raw, uncalibrated data. You want to see what Atlas actually looked like in March 2020, go to Archive, STCI, edu. Search for Observation ID OCDD01 and download the FITS files yourself. You'll need free software like DS9 or SAO Image to view them, but these are tools professional astronomers use daily. The learning curve is steep but not insurmountable. There are YouTube tutorials, there are online communities ready to help. And once you can read that data, you're not relying on anyone else's interpretation. You can see for yourself whether there's a secondary signature at 0.31 arcseconds offset. You can check the photometry. You can run your own analysis. Citizen science projects make this even easier. Zooniverse hosts Planet Hunters, where volunteers scan telescope data looking for exoplanet transits. They've found planets professional astronomers missed. The AAVSO, American Association of Variable Star Observers, coordinates amateur observations that fill gaps in professional datasets. Your backyard telescope might catch something Hubble pointed the wrong direction to see. Second, learn the tools. You don't need a physics degree to understand orbital mechanics. You need curiosity and patience. Start with free planetarium software like Stellarium. It shows you the night sky from any location on Earth at any time. You can track comet positions, predict when objects will be visible, understand how things move through space. Then graduate to orbit calculation software. GMAT, the General Mission Analysis Tool, is what NASA uses to plan spacecraft trajectories. It's free, it's powerful, it's got a learning curve like a cliff face. But once you understand it, you can model the motion of anything in the solar system. You can input the Atlas Companion's observed positions and calculate whether its trajectory matches natural motion or requires unexplained acceleration. You can verify or dispute the analyses we've talked about. For observations, amateur telescopes have become shockingly capable. A Celestron NexStar 8SE costs about $1.200 and can track objects down to magnitude 13 or 14. That's faint enough to see asteroids, faint comets, even some of Jupiter's smaller moons. Add a decent CMOS camera for another $500, learn basic astrophotography, and you're collecting data that would have been cutting-edge professional quality 30 years ago. Gennady Borisov discovered the second confirmed interstellar object, 2I/Borisov, using a telescope he built himself in his backyard in Crimea. Not because he had resources NASA doesn't have, but because he was looking at the right patch of sky at the right time with equipment good enough to catch something new. You could do the same. Third, join the community. This is where individual capability becomes collective power. Forums like Cloudy Nights and Reddit's Our Astronomy connect thousands of amateur observers. When someone spots something unusual, word spreads fast. Multiple observers in different locations can provide verification within hours, light pollution obscuring your view. Someone in a darker location might have a clear shot. The network of amateur astronomers worldwide now represents millions of dollars worth of observing capability operating every clear night. Professional telescopes have scheduled observing time that cost tens of thousands of dollars per hour. They can't afford to spend that time chasing maybes. But you can. Your time is your own. If you want to spend 3 weeks photographing the same patch of sky hoping to catch an anomaly, nobody's stopping you. And that's how discoveries happen now. Not through lone geniuses having eureka moments, but through distributed networks of people sharing data, checking each other's work, building collective knowledge that no single institution could match. Fourth, think critically. Here's the part nobody wants to hear. Most anomalies aren't anomalies. Most mysteries have boring explanations. Most times you think you've discovered something new. You've actually discovered a well-known phenomenon you just didn't recognize. So learn to identify red flags, claims without sources, appeals to authority without showing the actual data, unfalsifiable statements like, the government is hiding the truth that can't be tested or verified, explanations that require conspiracy when mundane explanations fit the facts. The Atlas Companion is interesting precisely because it has verifiable data, documented observations, and mathematical analysis anyone can reproduce. It's not someone's blurry photograph claimed to be a UFO. It's actual telescope data with timestamps and coordinates and measurements. That's the standard you should demand, not trust me, but here's the data, check it yourself. And when you check it, assume you're wrong first. Assume it's instrument error, or atmospheric distortion, or something you missed. Only after eliminating those possibilities should you start considering stranger explanations. The difference between conspiracy thinking and legitimate skepticism is this. Conspiracy thinking starts with a conclusion and filters evidence to support it. Legitimate skepticism starts with evidence and follows it wherever it leads, even if that means admitting your initial guess was wrong. Fifth, demand transparency. You're a taxpayer, assuming you're American, which means NASA works for you, not the other way around. When they classify scientific observations under ITAR without clear justification, you have every right to ask why. The Freedom of Information Act exists for exactly this purpose. Filing a FOIA request is free and surprisingly straightforward. You send an email to NASA's FOIA office requesting specific documents. They're required by law to respond within 20 business days. They can deny requests for legitimate national security reasons, but they have to explain why. Enough people requesting the same information sends a message the public cares, and silence isn't acceptable. Contact your representatives. Congressional offices track constituent concerns. If enough people from a senator's district call asking why NASA is classifying comet observations, that senator's staff will ask NASA the same question. That's how oversight works in a democracy, not through dramatic confrontations, but through steady pressure from citizens demanding accountability. Support open science initiatives. Preprint servers like Arxiv let scientists share research before formal publication. Open access journals make papers available without paywalls. These movements ensure that science belongs to everyone, not just people who can afford expensive subscriptions. The bigger picture. The companion object next to Atlas might remain a mystery. It might get explained next week when someone spots the obvious flaw everyone missed. It might turn out to be the most important astronomical discovery of the century. We don't know yet. But here's what we do know. The universe doesn't belong to institutions. It doesn't belong to credentialed experts or government agencies or anyone who claims special authority to decide what you're allowed to understand. The universe belongs to anyone willing to look up and ask why. To anyone with the curiosity to dig through data archives at midnight because they can't stop wondering. To anyone who refuses to accept "trust us" as an adequate answer when evidence suggests otherwise. NASA might have the best telescopes. They might have billion-dollar budgets and teams of PhDs, but you have something more powerful. You have questions that can't be classified, curiosity that can't be embargoed, and the fundamental human drive to understand that no bureaucracy can suppress forever. The Atlas companion, whatever it was, flew through our solar system in 2020 and continued on its way. We can't follow it. We can't catch up to it. We missed our chance for closer observation. But the next mystery, the next object that shows up in telescope data doing something it shouldn't, that one might still be findable, still be trackable, still be waiting for someone to point their backyard telescope at the right patch of sky at exactly the right moment. Will that someone be a professional astronomer with decades of experience, maybe? Or will it be you, reading this on your phone at whatever time it is where you are, thinking, I wonder if I could actually do that? The sky's still up there. The stars aren't going anywhere. And somewhere between what we know and what we're allowed to ask about, there's a truth waiting to be found. You just have to be curious enough, stubborn enough, and maybe just a little bit reckless enough to go looking for it. Thanks for listening. Keep looking up, keep asking questions, and remember the universe is under no obligation to make sense to us. But we're under no obligation to stop trying to figure it out. Wherever you are, whatever time you're reading this, good night and clear skies.